Hi everyone, this is Jan David from SoundMorph, and I'm here today to give you a preview of the collaboration we are currently working on with Epic Games to provide you with a free pack of MetaSounds created by us here at SoundMorph, and also give you a few tutorials on how some of the sounds were built. So before we jump into it, I just want to share a bit of our history. We started SoundMorph, me and Jason Cushing, around 10 years ago while we were working on a game together. And at that time, we felt that the design sound libraries on the market were not up to the quality level of AAA games and Hollywood movies. And during crunch time, when we sometimes had to create 100 sounds in a week, we really wished there was some sound libraries good enough out there to be used directly in our game. So we decided to do it ourselves, make our own company, and sell sounds that we felt were good to go in a project without the need to do anything to them. And while we were working on our first library, Users of Tomorrow, which is a UI sound library, I built 3 patches in MaxMSP to help me create sounds for it. And I realized once we were done that it would be really cool if we built a standalone application with the patches and include it for free in the library. And we called the app Galactic Assistant. And from there on, we created other applications and plugins targeted at sound designers, like WaveWarper for creating whoosh sounds, TimeFlux for creating slow motion sound effects. We also created a reactor ensemble called Evil Twin, and our first audio plugin is called Dust and is a binaural granular synthesizer. But while I was working in the video game industry, I learned how to use Unreal, and being familiar with visual programming software like Max and Reactor, I felt really comfortable using blueprints and really enjoyed it. And I always told myself like it would be really cool if an audio programming software would look and behave like blueprints. And so when I saw MetaSounds for the first time, I was really excited, and even more excited and honored when Epic Games asked us to do this collaboration. My goal for the pack was to use simple ideas that really helped me initially when I started programming, but ideas that I'm still using today and concepts that can be used in more complex situations. So let's take a quick overview of the pack. So the first folder you'll see at the top, called Utility Graph, contains patches that have been used in multiple other graphs. It contains generic building blocks that can be reused, like bubbles, singing glass. Here's a metal bell. The metal bell sound has been used in a couple of other patches, like this teleportation sound, inspired by a certain popular game. And here's a healing sound that uses the bubble graph we just heard. We have a weather system which contains a rain, wind, and thunder simulation. Here's a light cycle sound based on a shepard tone, mixed with a shepard filtered noise, which I'll show how to create a bit later. We built a graph based on some parts of Galactic Assistant to create UI sounds. We've also completely rebuilt WaveWarper 1 and MetaSounds. We have some retro 8-bit sounds. Here's a sci-fi gun sound. We also did some MetaSounds based on our free droid app inspired by a small robot. Here's some robot beeps. Here's some vocal expression sounds. And also some whistling sounds. Alright, so I'll start the tutorial by showing you how the talking robot sound was built. Let's start by building a basic FM synth. I'll use a patch for this. A patch is a graph that can only be used in other graphs. It does not make any sound on its own. Let's create the inputs needed. We'll need an input for the carrier frequency, one for the harmonic ratio, and one for the modulation index. So let's drag them in our patch. To create a new node, you can simply right-click to open the nodes menu and browse, or start typing to search for a node. Alternatively, you can drag a connection cable out and start typing. And this way of doing frequency modulation, instead of just connecting a sine wave into the modulation input of another, is based on an article by John Chowning. It gives you the ability to control the harmonic relationship of the sidebands, which are the extra frequencies generated by the frequency modulation, and the amount of them, so basically controlling the brightness of the sound. Okay, so let's create an output for the audio. And let's create the main MetaSound source. I'll delete the one-shot interface for now. We don't need it yet. And now if I open the node menu and search for basic FM, you can see that the patch we just created can be used inside any other graphs. I'll create inputs and test it out. Okay, so I should be getting sound here, so something is wrong with our FM patch. You can open it up by simply double-clicking on it. Okay, so I forgot to add the carrier value to the output of the modulator here. And while I'm back here, I'll take some time to clean up. Try to make your graph as clean as you can as you go along. It will be much easier to understand if you open them later on. Sometimes I open a graph just a couple of days after I made it and I have no idea what's going on. And it's also obviously a really good habit if you are working with other people so they can understand what's going on in your graph. First thing you can do is align or distribute the nodes. You can also straighten the connections. You can add reroute nodes by double-clicking on a connection line if you want to prevent connection lines from overlapping nodes. But one of the best ways to organize your graph is creating comment boxes by selecting the nodes and pressing C on your keyboard. A great thing about comment boxes, beside adding a description, is that you can move the whole section around. You can also change the color of the box if you like. And last thing you can do is add descriptions to inputs and graphs. Those will appear as pop-ups in the main graph when you mouse over. Okay, so for the frequency, we need it to fluctuate randomly. We can use the low frequency noise for this, which generates a random smooth signal between two values. Let's try 200 to 1500 Hertz. I'll create an input for the rate. I'll rename rate to talking speed. And I'll create inputs for min and max frequencies. All right, now I need something to control the duration of the sound. I'll use an ADSR envelope. This will be used also to create a small fade in and fade out on the sound. So let's put a small attack and release of something like 0.1 seconds. No decay. Sustain at full volume. And we want to trigger it when the sound starts. And to trigger the release, we'll use a trigger delay. And let's promote the delay time. This will control the duration of the sound. And now I'll re-add the single shot interface to stop the sound once the envelope is done. And let's multiply the output by the envelope. Okay, let's try it out. Okay, so right now you'll notice that each time the sound is triggered, the frequency is different. And this is because the seed is set to -1, which causes the noise to select a new seed every time the sound plays. What we can do is promote the seed input to a variable, and now we can choose seed like, let's say 45. And now the sound is the same every trigger. And if we don't like it, we can try another seed until we find something we like. And now I would like the option, instead of having a FM sound, to have a whistling sound. I'll start with a white noise and use a biquad filter. And set the type to bandpass. For the frequency, it also needs the output of the low frequency noise here. So I'll promote it to a variable so that it can be used anywhere in the graph. And for the bandwidth of the filter, I like to use Q values instead of bandwidth. There's a conversion node called filter Q to bandwidth you can use. And we need a pretty narrow band here, so I'll put something like 100. And we'll duplicate the filter to really isolate the frequency. So now there was a lot of filtering, so we'll need to increase the gain. I'll multiply the output by around 30. And let's try it out by replacing the FM synth. Great. Now I would like to be able to select between the FM synth and the whistling sound. I'll add a bool input, which is a true or false value, and call it is whistling. So first thing we need to do is use a compare node. I want to compare it at the start of the sound. Compare it to a true value. And depending if it's true or false, we'll need to select either the FM or the whistling sound. We can use a trigger route. We want to route two audio signals. So now if is whistling is true, this audio will be used. So let's connect the whistling sound there. And if it's false, the other one will be used. Let's plug that on the envelope and test it out. So is whistling is false right now. And we hear the FM synth. And if it's set to true, we hear the whistling sound. So awesome. So now if you want to do presets, simply right-click on the source graph and select Create Preset. And from there you can override the default of the inputs. And if you want to rearrange the input order here, you can change the sort order value in the input details panel. The higher the sort order value is, the lower it's going to appear in another graph. Okay, so now let's build a shepard noise graph of the light cycle. The graph is a shepard tone, but instead of using sweeping oscillators, we'll sweep filter frequencies on a white noise. A shepard tone is an audio illusion that gives the impression that the sound is constantly going up or going down. It's considered the audio equivalent of a barber pole, where it looks like it's constantly going up. And the way it works is that you have at least 4 octave sweeps layered together. In this example, the lowest one goes from A1 to A2, the second one from A2 to A3, the third one from A3 to A4, and the last one from A4 to A5. And when it loops, this layer will seamlessly connect to this one because it starts where the other one ended. But the first layer start doesn't connect with anything, so it needs to fade in. And also the end of the last layer does not connect to anything, so it needs to fade out. So let's create a new graph. And this is a loop, so we don't need the one-shot interface. First thing I'll do is create an input for the bass frequency. And set a range of, I'll set a range from 20 to 1000 hertz. And set a default to 300. And I'll create variables for each frequency needed. And with 4 layers, we need 5 frequencies. I'll bring the bass frequency in. And let's set the frequency variables. Okay, so now I drag the variable in, but this is to get the variable. If you want to set it, you need to hold shift while you drag it out. So frequency 1 is the same as the bass frequency, and then frequency 2 is twice the frequency 1, so we'll multiply it by 2. And then we just keep on multiplying by 2 to get the next frequency. So now we need to control all the frequency sweeps. I'll use an AD envelope and set the decay to 0 and set the envelope to loop. I'll promote the attack to an input, and this will control the duration of the sweep. I'll set a range from 1 to 10 and set a default of 5 seconds. I'll promote the output to a variable and call it ramp. And also you can debug a float while the sound is playing by hovering over the output with your mouse. As you can see here, it goes from 0 to 1 in a loop. I'll create a noise for the filter inputs. And all right, let's create the first layer. I'll use a biquad filter, plug in the noise, and add a filter Q input control. I'll set the range to something pretty steep, like 10 to 100. And same thing with the previous graph, I'll convert it to bandwidth and promote it to a variable. I'll just connect it and I'll need to set this to bandpass. To control the cutoff frequency, we'll use our ramp, but it goes from 0 to 1 and it needs to go from frequency 1 to frequency 2. The node we can use for this is the map range node, which will scale and offset the ramp value for us. And let's duplicate this 3 times for the other layers. Okay, so let's set the map range outputs, minimum and maximum values. The first layer goes from frequency 1 to frequency 2. The next one from frequency 2 to 3. The next one from 3 to 4. And the next one from frequency 4 to 5. And we need to mix those 4 layers together, so I'll add a mono mixer 4. And remember that we need some fade in and outs on the outer layers. The first one needs to fade in. We can use the ramp for this since it's going from 0 to 1. And the last layer needs to fade out. We can also use the ramp, but we'll have to invert it by subtracting it from 1 so that it goes from 1 to 0. Okay, let's take a listen. Great, so now I would like to be able to make it go down. I'll add a bool input and call it is going down. Like in the previous example, I'll use a compare node, check if it's true at the start of the sound, but this time I need to route 2 float values. So if is going down is false, we'll use the output of the envelope directly. And this output will become the ramp value. And if is going down is true, we'll invert the envelope by subtracting it from 1. Okay, let's check it out. Alright, it works. The reason I decided to show the shepard filtered noise instead of the classic shepard tone is because it's seen less often and it shows a different way the concept can be used, like as an engine in the light cycle example. You could also layer real sounds on top of it to add realism if you wanted to. One last thing I would like to show you from the pack are the elastic audio players in the utility graphs folder. Those are the included wave player nodes, but have the added ability to time stretch the wave file input. If time stretch is active, the speed and the pitch of the sound can be controlled separately. Alright, let's look at how this works. I'll use a mono wave player and select a wave file. And set it to loop. And let's promote the pitch input. And set a range from -24 to 24 semitones.
Everything we do.
And if I change the pitch, as expected, the speed will also change.
Everything we do.
What we can do is add a delay pitch shift. And invert the pitch value by multiplying it with -1. So for example, if the pitch is set to +12 semitones, this will counter pitch it back down to 0. But now we can control only the speed of the sound.
Everything we do is for the purpose of altering consciousness. Everything we do is for the purpose of altering consciousness. Everything we do is for the purpose of altering consciousness. Everything we do is for the purpose.
But the problem is that we are controlling the speed using semitones. I'll add an input called speed ratio to control the rate. And I'll set a range of 0.25 to 4 with a default of 1. Now what I would like is, if this is set to 1, the speed should play at the original rate. If it's set to 2, then the speed should be doubled. And if it's set to 0.5, then it should be playing at half the speed, and so on. And the way we convert this knob to semitone is by taking the log of the value in base 2, and then multiplying it by 12, because there are 12 semitones in an octave. And let's replace the pitch knob with this. So now if we set this to around 2,
for the purpose of altering consciousness.
It plays twice as fast.
Is for the purpose of altering consciousness.
At 0.5, it plays half as fast.
Is for
and at 0.25, it plays at a quarter of the original speed. And now if we want to control the pitch separately also, we can simply add it to the inverted pitch shifter value.
Everything we do
is for the purpose of altering.
And now we can pitch shift without changing speed.
Do
is for the purpose of altering consciousness.
And if you want the ability to have the original behavior of the wave player, we can create a bool input. And let's call it time stretch. And add a compare node. Route 2 audio signals. So if time stretch is true, we will use the pitch shift output. And if it's false, we'll use the output straight out of the wave player. And we will need to route the pitch value. I'll use 2 floats. So if time stretch is on, we'll use this one. And if it's false, we'll use the pitch knob.
Everything we do is for the purpose of altering consciousness. Everything we do.
And now we get the original behavior of the wave player.
Everything we do
is for the purpose of altering consciousness. Everything we do is for the purpose of altering consciousness. Everything we do is for...
Alright guys, that's it for today. Really hope you've learned something. Stay tuned for the release of our MetaSounds pack on the marketplace, which should be released really soon. You can subscribe to our newsletter at soundmorph.com to get notified once it's released. Alright, have a nice day.